In this video, we're going to solve question 6 from page 14 of the Learning Outcome 3 course notes for the unit Statics. In this question, we're asked to use Bose notation to carry out nodal analysis to identify the magnitude and nature of the internal forces within the members of this structure. And we'll do a little bit of preliminary work to set this question up in order to be able to use different analytical techniques, including Bose notation, to solve the problem. The first thing we'll do is we'll label our reactive forces R1 and R2. Because we're going to be solving these first in order to get our starting point for the question. We're also going to label the spaces in between forces with a different lettering system so we can have vector names for each force acting within each member. So starting up in this space up here, we'll use the letter P, and this is representing the force that runs all the way around from the left-hand side of R1 up to the 104 kilonewton force. Internally within these triangles, we'll label the spaces Q, R, and S, and we'll label the space between the 104 kilonewton force all the way from its right-hand side down to the right-hand side of R2. That's going to be space T. And then finally, we'll label the space in between our two reactive forces as U. So this allows us to make a little table for our framework, so we can include all of the members for us to record their forces. We'll also name all of the vectors which are going to be representing these members in our table. So we'll have 4 headings here. We'll have the force, and these forces will take their names from the nodes in which the members span. We'll have the vectors, and each vector's name will be from the spaces on either side of a member. We will have the magnitude of the force, and we will also have its nature. So let's set out our table just now. We'll start off with each node in turn, and then we'll list any additional members we need to consider. Starting at node A, it is connected to B, so we'll have the force AB, it's connected to E. Node B is connected to A, we've got that covered already. It's also connected to C and connected to E. Move to node C, and that's connected to B, we've got that covered. And we'll include CD and CE. And moving on to node D, well, that's connected to node C, but it's also connected to node E, which we haven't added yet. And node E is already represented. Its 4 members that connect to that node are already listed in our table. We also want to include in our table the reactive forces R1 and R2, because these are currently unknown to us. Now, we can also label each of these with a vector. Now, inside each member, we'll be having forces acting in both directions, whether they're under compression or tension. Then, depending on which node we're considering in a member, they will either be acting one way or other along the length of that member. So we'll just label the vectors alphabetically just now, but we will use them interchangeably, so PQ and QP, depending on which node we're considering. So in each case, we're going to be looking at the space on either side of the member, and we'll get our vectors as follow. AB will be vector PQ, AE will be vector QU, BC will be vector PR, make that R look a bit more like an R there, BE will be vector QR, CD will be vector ST, CE will be vector RS, DE will be vector SU, and we also have vectors to represent the reactive forces as well. So R1 will be vector PU, and R2 will be vector TU. I'll try and make it absolutely clear when it's a T and when it's an R. And we have a space to record the magnitude of each vector as we determine these analytically or graphically. And we'll have a column for nature, and that's to determine whether they're under compression, and so are struts, under tension, and so are ties, or whether the forces are balanced in such a way that there's no internal force in the member and it is in fact redundant in the structure. If that occurs, we can record that there. One thing we can put down immediately, though, is there's no need to include a nature for either of our reactive forces. That is only something that applies to internal forces, and they are external forces due to the reaction in the supports to the loading of the beam. And that's what we're going to deal with first of all in this question, is the reactive forces. The reason we need to look at the reactive forces first in this question is if we observe our diagram, we currently only know one applied force, which I'll circle in purple here. And this node has 3 members and 1 applied force, so 4 forces in total. That means 1 known and 3 unknown forces at one point. And Bose notation can only be used for up to a maximum of 2 unknown forces. So until we establish another force in this question, we have nowhere we can start with Bose notation, because the only one known force that we have connects a node with 3 unknowns. But if we observe both of our reactive forces, they connect, both of them, at nodes which have only 2 other unknowns other than the reactive force themselves. So if we can obtain these reactive forces in the way that we've done previously, using moments and balanced vertical forces, then we have a starting point for Bose notation, which is why that's what we're going to do here. Now, a sticking point in this question might appear to be that we haven't been given the length of any of the members in the question, but we are actually able to determine these moments without knowing any length at all. And the reason we can do this is because we can observe that the base of both of these equilateral triangles must be the same length. So both of these blue lines are the same length here, because the triangles are similar and the way that the shape is, because they both share a side with the middle triangle, and that sides are all the same length, so the side length must also be the same on the 2 triangles which have space Q and space S in the middle of them. So because these 2 blue lines are the same, we know that whatever the distance between R1 and R2 is, it's the length of these 2 blue lines. But also we know equilateral triangles, that if we have them with the base flat and against the horizontal, the other point is going to be above the halfway point in the triangle. So what we can also say is these 2 green lines from the midpoint of our structure divide into 2 equal parts as well. So we don't know how long this structure is, but we know where the force is being applied in relation to how long it must be. So if we decide to say that the length of our structure is x, then we can use the position and length of the sides of our triangles in order to find the forces based on the moment. Now, this might not seem obvious just now, but we're going to do it, and you'll be able to see how exactly we managed to solve this without any need to know the exact length of the beam, as long as we know these proportions, which I've marked out on the diagram. So let's have a look. We know when we consider the moment, we consider the moment a particular point. So we are going to consider the moment at node A, and that's going to be equal to 0. It always is. The moment's always equal to 0 in a static structure. So what does this mean? Well, it means that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So what clockwise moments do we have here? Well, looking out from point A, everything's to the right of that, and we've got a downward force of 104 kilonewtons acting out to the right, so that's a clockwise moment. So we can say here, one clockwise moment, 104, and the distance of 104, well, it's 3/4 of the way along the beam, because if we go from point A to point E, that's halfway, and we go from point E to that dotted green line, that's halfway of the remaining half, so that's 3/4. So we can say that 104 kilonewton force is applied at 3/4 of x, whatever x is. In terms of our anti-clockwise moments, there's only one force acting other than the 104 kilonewton force, and that's R2, and that's acting up the way and to the right, which means it's going to be our anti-clockwise moment. So we have a force R2, and it's acting at the full distance x away from point A. So we've got R2 times x. Now this means that if we do 104 times 3/4, we have 78x is equal to R2x, which means it's a simple matter of dividing through by x to give us that R2 must be equal to 78 kilonewtons. So it doesn't really matter when we've got a particular problem like this what the length of the beam is, as long as we can work out which proportion of the beam. We knew that that force was 3/4 of the way from A, which allowed us to find out the value of reactive force R2. In most problems, we will give you the length of members or some indication of dimensions in a structure, but this example proves that if you have enough information, you don't actually need a value for that, because the forces at the end of the day we're calculating, not length. Now, because we have R2, we can use another fact from static equilibrium, which is that the total upward vertical forces must equal the total downward vertical forces. And so we'll say that R1 plus R2, so we look at our diagram here, we can see the only two forces, our two reactive forces, are equal to 104. That's the only downward external force acting on the structure. And so substituting in our value for R2 we've just worked out, R1 plus 78 is equal to 104. And so R1 must be equal to 104 minus 78, which is 26 kilonewtons. So returning to our diagram, we won't need all these measuring, so I'm going to remove them for the second part of the question. The main part where we use Bose notation, but I can remove all of this in here. And add to the diagram what we know about the forces. The R1 is 26 kilonewtons and R2 is 78 kilonewtons, and that's going to give us a starting point for Bose notation. And I'm going to record these magnitudes here in our table as well. So we have 26 kilonewtons for R1 and 78 kilonewtons for R2. I'm going to have two starting points, which will allow us to make use of Bose notation and analyze the rest of the structure. So we proceed to use Bose notation to begin to analyze our structure. We can start at 2 points here, either point A or point D, because these are the nodes in which we have only two unknown forces, and both are equally valid choices. You will be able to build up a model of the structure and use your scale diagram in either case in order to obtain values for all the remaining members and their internal forces and directions. We're just going to choose to start at D here, and part of the reason for that is because from D we can move on to C and tackle a slightly more complicated node in terms of having 4 points connecting to it rather than just 3, and build up a picture of our structure from there, working around our diagram. But really, after your first choice of node, as long as the next node you move to has only two unknowns, you can choose to move through the diagram in whichever order makes sense to you. But we'll do one here that will work. So we're starting off at node D. And in this video, what we'll be doing is building up a single scale diagram for the entirety of the structure. So we will have an individual space diagram for every node, like this example here for node D, but we will be building up one scale diagram that has all the vectors on it. So there will be some overlap, but we're using this to try and show which forces apply where. as best as possible. So this is node C, and we have some information about this already. We know that this force here is 78 kilonewtons. We know this angle here is 60 degrees. And of course, we know the names of the spaces as well. This is space S, space T, and space U, as we can see on the diagram here. And so we have to label our vectors according to the according to the spaces on either side of them, with each one taking its name from the spaces on either side. Now, there's not a particular order we have to label our first vector in, but the order in which the others is labelled afterwards is important, and we'll see why. So let's start off by labelling the vector that we know about, the reactive force, and we'll label this TU. Now, this node is ecstatic equilibrium. So what we'll be hoping for the forces in this node, well, we're hoping our diagram looks like this, is that we have a chain of vectors taking us back to our starting point, so that there's no resultant vector acting in this node. So that means we're drawing a vector diagram, which in this case with three forces will form a triangle. So we expect the three vectors to join tip to tail, which means that this vector here will therefore be US, because it will start with the end letter of another vector, and this vector up here will be ST. And this will help make sure our diagram works, our labeling is consistent. And when we're building up a full-scale diagram, it's important to try and do this, otherwise we can end up getting ties and struts confused later on, which can sometimes make things not seem to make sense and throw off some of our later answers. So taking care at this stage does matter. So let's begin to draw this diagram. The one thing that we know to begin with is the force whose magnitude we have, and this is the vector TU. It's acting vertically upwards, and it's got a 78 kilonewton magnitude. So we're going to use a 1 centimeter to 1 kilonewton scale here, and as best as is possible, I will draw this on the whiteboard using the ruler. I'll take the solutions we obtain from the course notes because there are some limitations to what can be achieved on the whiteboard. And as I mentioned, every vector we deal with is going to have a different color. There'll be quite a few vectors, but I think we've got enough colors in the pen palette to make that work. So we'll start off by making red as our first choice. The vector TU is going to be 7.8 centimeters long, representing 78 kilonewtons. I should say as well before I do this, properly in Bose notation, we always do a little crosshair as our starting point. I suppose this is not critical, but since we're doing it on a whiteboard and we can match it onto a grid, but let's be consistent with the methodology from the course notes. We'll draw this line up here. We can quite accurately draw up to 7 centimeters, and then I'll do my best to have a good estimate at 7.8. That's pretty close to 7.8. I've got kind of to go to 7.75 and nudge it a wee bit along. But it should still look pretty good on the diagram. So we've got a line here that is representing vector TU, and we'll label this accordingly, T and U, to represent the direction that we're moving in here. And we can write on this as well, this is 7.8 kilonewtons because we've measured that out already. The next stages in Bose notation have us join our other two vectors at the ends of our first vector where they match. So the vector US will run through point U, and the vector ST will run through point T, and they'll both meet somewhere, they'll both cross over and meet at some point T. So what we know about the vector US, if we want to begin with that, is I'll indicate the direction of our travel here with a little arrow here just now. I'm not marking these permanently on the diagram because in our full-scale diagram here, we'll be having vectors traveling in different directions at different times, although the vector TU will always travel upwards because it's not an internal force, it's an external force. So let's start off by in a different color for vector US. And to draw this on our diagram, we set our ruler horizontally and we draw a line that just must connect to the tip of vector TU, because it does connect to point U, but it's not clear immediately which direction it goes in. So we draw a line across through here. Somewhere along this blue line is point S. Now, you'll probably, if you've done a few of these now, know that it's going to be out to the left, but to save ourselves having to second guess ourselves, we start off by just drawing a straight line out. Now, vector ST connects to point T and it acts at an angle that's 60 degrees above the negative direction of the horizontal line. So we draw a little dotted horizontal line here and measure up 60 degrees. This is the direction the vector ST has to run in. So let's get 60 degrees marked in here. And we draw a line. Now, we could draw a line all the way through point T in both directions, but we know it needs to go and join up to vector US. So we're allowed to, I could draw a line, I'll draw it and remove it. I could draw a line like this, saying, oh, where does this vector go? It must go somewhere along here. We know it's not going down the way. We know it's going up to meet the line US somewhere, so I won't draw in a green line like that. Instead, what I'll do is I'll start at the crosshair and draw a line up that stops at point on the blue line, which is going to be that point S, because one vector is US, one vector is ST, so we can mark this in as an S here. And so now that we know that the point S, we can remove the rest of this blue line because we know where the vector US lies in our diagram. I'm just going to carefully remove the rest of that line there. And we can obtain two different pieces of information about each of these vectors from this. First of all, we can obtain the direction. Remember, we have to move in one circuit to go from T back to T. So if we're going from T to U, it means we're going from U to S. That means we're coming back down from S to T. And we can mark these directions on our space diagram here. So this horizontal vector US must be acting to the left. And our diagonal vector ST is acting down towards the node. And this tells us two things. It tells us that ST, since the internal force is acting towards the node, that means that it must be a strut. And strut's internal force act towards the node to counteract and balance the forces of compression which are acting on it, because the forces of compression act on the end of the member, so the internal forces act out the way. This also tells us, because the internal force is acting away from the node for vector US or SU, that the member DE must be a tie, because those forces, again, are counterbalancing the tension that's pulling on the ends of the member. So right away, we have the nature of two of our forces. We can also gain some other additional information about our members from this as well. We can find out their magnitude. Now, as I said, I'm going to, you can get your ruler out, and I'll measure, may as well measure ST since I've got my ruler out here. And if I line this up, I'm going to see this as 1, 2, 3, 4. I think this actually might be accurate. If we measure along here, we're going to see that we have 1, 2, 3, 4, 5, 6, 7, 8, a 9 centimeter length of line, which corresponds to a 90 kilonewton magnitude, and that actually is what the answer is in the course notes, so we can go with that. Where there's any variance, so if I've done this correctly, it should be minor, and the course notes will stick with that, so the rest of the question works out the same way. And D, represented by vector SU, well, if we measure that, we should get a line which is 4.5 centimeters long. I'll just measure that just now. I think mine just about manages to come in at 4.5. There maybe my line's a little bit short, but 4.5 centimeters, meaning that in our scale of 1 centimeter to 10 kilonewtons, that the magnitude of the internal force in member DE is 45 kilonewtons. So we can include that in our table. And we can also go back to our main diagram here, and we should record the direction of the internal forces, because this is going to be helpful with the remainder of our nodal analysis. Because we've identified that CD is a strut, we know that it's acting in towards that node, but it also means the direction of the force up at node C is acting towards node C. And similarly, the member DE, the forces act away from the node, and that happens at both ends. So we now know something about one of the forces at node E, and we know something about two of the forces at node C, because we now have information about CD, and we also have this external force of 104 kilonewtons. We still have two unknowns, the members BC and CE, but that's enough information in order to move on to node C. I've labelled this node C to begin with. I'll just fix that. So we began with node D in this question. I'll add a wee note about that in the video. We can move on to node C now and carry out the analysis there. So we start off as always by drawing in a space diagram for this node. And what we have is we have three members that are coming into contact with each other here. I have an external force being applied. And we've been told already the external force is 104 kilonewtons. If we look at our diagram, we can see that these angles must be 60 degrees here. In fact, we're told this, and as a result of this being an equilateral triangle, this angle here is also 60 degrees. And what we've just learned in the previous part of the question is that this vector, which is for member CD, has a magnitude of 90 kilonewtons. So we can add this in here as well. The other thing we know about all of our spaces is that we know what all our labels are here as well. So if we go back to our diagram, we can see this up here is space P, this is space R, this is space S, and this is space T. And so this gives us a basis of labeling our diagram. Now we'll start off with the vector we've just dealt with. We called this ST in the last example, so we're going to call it TS this time round, and that's simply because it's acting in the opposite direction, the force this time. These are things which will write themselves if you make a mistake. You'll see it when you come to the diagram, but we want to start ourselves off the way we mean to continue by calling this TS here. So we can work our way around, and so we're going to call this one SR, we're going to have RP, and lastly up here we'll have PT. And we can, from this, we can build up a picture of where all of our vectors are going to fit onto the diagram. So let's have a look. Going back to our scale diagram, I'm going to remove these arrows. And the reason I'm going to remove them is because these were how the arrows applied at node D. But we know, for example, already, and I can mark this on, that our green vector here, which represents member CD, if we're looking at member C, then the force is acting in this direction towards the node. So which node we're thinking about does matter when considering the direction of the forces here. So we've already got TS, as it now is, marked in this diagram. We also need to include the other vector we know something about, which is vector PT. And vector PT acts vertically down the way, ending at point T. So this is going to run through the point U on our diagram and go all the way to point T, because we know the line UT is 78 kilonewtons, so it's 7.8 centimeters. So we need to draw a vertical line downwards that ends at point T, that's 9 centimeters long, sorry, that's 10.4 centimeters long, to represent the external force applied at the top of this structure. So this is where these diagrams can be a little bit messy, and that's why sometimes even with color we can make our lives a little bit tricky here. But as long as we keep the lettering in place, we still know where point U is. And sometimes what can be helpful, in fact, maybe I will do this exact thing in this scenario here. Actually, let's keep this the way it should be. I should have marked on that was 60 degrees here as well. I'll leave that diagram exactly as it was for node D, and I want to copy the diagram and add to it. So this was the order of our forces for node D. So rather than immediately vandalize the diagram that we have here, what we're going to do is just make a copy of this diagram, and we'll add on our information for node C to a new diagram. And this was something I actually meant to do in class when we were doing one of these examples and didn't realize at the time. So I'm caught myself this time, and we'll add it in. So what I will do is take away those arrows again, because like I said, that is a direction that these forces act in relative to node D. We're considering node C. And so we know that our vector TS is acting in this direction, and we know we need to include a vector PT starting at P and going down the way towards point T, because that is where it ends based on our lettering, which corresponds to the order in which these vectors connect. So if I measure a line of 10.4 centimeters up from here, that will be 2, 4, 6, 8, 10, and then I'll do my best to mark on a further 0.4. I don't think that's too bad. We know that this force must be acting down the way. And further to that, we know that this point up here, the starting point, must be point P. I think we'll just make that slightly higher up because there's a line running through it. Now this is where we can, and actually to keep this, I'll mark these colours on the space diagram so you can see which vectors they correspond to as well. So there's purple and green. So we have one line RP, which is going to be a horizontal line running through P, and we have another line SR, which is at an angle acting through point S. So we can draw both of these onto our diagram just now. So let's pick another colour. We'll pick orange for this one and get a horizontal line, because we know the vector RP, which represents member BC in our main framework diagram. It has to be somewhere on this line here, because it's horizontal, because the member is horizontal, and it has to connect to point P at one end. So that's going to be our vector RP. And we know we've got a vector SR, which is joined to point S, and we know that it acts at an angle of 60 degrees to the positive horizontal direction. So that's 60 degrees, if you like. We can use the line SU to measure this up here, because it's 60 degrees up, starting at point S. So we measure an angle of 60 degrees. I'll indicate that in a second. And this needs to join point S to the orange line. So I'll change our colour to, we'll use cyan for this line here. And this is the vector we have here. So I can take the ruler away. I'll just indicate where that 60-degree angle I measured was. It was between these lines here. And we follow our, I'll tidy this orange line up first of all. Move all of that. This point where the orange line and the cyan or light blue line connect must be the point T, because we had one line that was horizontal from P to T, and one line which was acting at an angle upwards of 60 degrees from S to T. So they must Be like, so I've been confounded again by my lowercase r's. This is point R here. The T's already dealt with, so apologies for that. This is PR and SR, these two lines. There we go. It's a little bit clearer. So PR and SR. And what directions are vector heading in? Well, we know that we've come down from P to T and up from T to S. Those forces are given before we even started drawing. Because that means if we're going around in a circuit, we must be going up from S to R, not T, and then along from R to P, like so. So that's the direction of these two additional forces we've identified. And so we can mark these on our space diagram. The SR must be heading up towards the node, making it a strut, and RP is also heading towards the node, making it also a strut. So let's take this information about the nature back to our table before we start measuring. So if we remember, SR represents the member CE. So we've worked out here that CE is a strut. And our other vector, which if we remember is called RP, that represents the member BC. And we found out that BC is also a strut, so we can record that in our table as well. And strut's a challenging word for me because I'm taking my T's and my R's, so that's a much better, strut. And now we need to measure the magnitude of both lines of our diagram. So taking our ruler back over here, I'll do my best to measure this off. The light blue line looks to me like it's about 3 centimeters long, which makes it 30 kilonewtons, which is indeed what the answer would have us say it is. And I think the orange line looks like it's about the same length, but let's use a ruler anyway rather than estimating. And that's also 3 centimeters or thereabouts in my ruler. Now remember, when you're doing this, be a bit more accurate than I'm being. You should be able to get quite a good measurement, and don't just assume because two lines look about the same length that they are. Although that does commonly happen in these structures where we use equilateral triangles, it's still best to be thorough. And even if you think they're slightly different, remember, within a certain level of accuracy, we are quite forgiving. So we've identified the magnitude of both of these internal forces as 30 kilonewtons. So that leaves us with 3 members left to analyse, but we've actually managed to achieve quite a lot with our diagram already. So let's go back and add this information to our diagram. What we've learned is that both of these are struts, which means we're going to have our internal forces acting towards these nodes here and here. So we have 3 forces left to identify and 3 nodes that we haven't looked at either. Now, if we make our choices well, we can avoid having to analyze all the nodes. We can get all the information we need from nodes B and E because they're both connected to A, so we will have all the information we need to analyze these nodes, to get the information about the members from these nodes here. So, and we can't do anything with, oh, we could actually analyze node A. Tempting it is to do that and start off in a separate part of the diagram. We'll continue to progress. We should always pick a node next that shares at least one of the vectors we've drawn in our diagram already. Otherwise, it's not possible to continue our scale diagram. So we're going to look at node E now. We could equally have picked node B here, but we're just going to pick node E, so we have to make some kind of choice. So we'll go down a bit. What we're going to do, we're going to take copy our diagram and add to it further. So node E, and I'm working from the course notes here, so I can draw in node E just now like this. We have these 4 forces coming together here. And let's remind ourselves what we know about this space. Before we even get into adding them, we know both of these angles are 60 degrees. And actually one in the middle has to be 60 degrees as well, although I don't think we'll need that fact. We know from our diagram here that CE is a strut and DE is a tie. So we're going to have this force acting in this direction, this force acting in this direction. CE we've worked out is 30 kilonewtons, so that's the size of this force here. And DE we worked out previously was 45 kilonewtons. So we know two forces and the directions. That's enough of a starting point. Further to that, we also have information about what we've labelled all of these. So we've got the spaces, and the spaces here for our main diagram are Q, R, S, and U. And so we're going to label all of these vectors according to the directions that they've been given previously. So if we look at the vector, the 30 kilonewton vector between spaces R and S, when we encountered this before, it was acting up the way because it was acting towards node C. Here it's acting down the way, so we're going to give this the name RS rather than SR, because it's acting in the opposite direction. And this is important, otherwise our diagram will begin to become a bit mixed up. So this is RS. And similarly, the vector between spaces S and U, when we dealt with this and it was heading away from the node, it was a vector US. So here it's SU heading away from the node, but a different node this time. And that's a clue that things are working out, because we would expect, having got a vector called RS, we'd have another vector beginning US, and that's a good sign. It means that these vectors are correctly labelled relative to each other, and there's then a good chance the rest of it's going to fit together. But I've just done, because this is where we've got the vector between R and S heading down to the left, I've just reversed the labelling from where we encountered it previously, where it was heading up and to the right. That's that cyan line we dealt with in the previous question. Well, this time we're heading down the slope, so the vector should be labelled in the opposite direction. We then can label the rest of our vectors because they've not been encountered yet. So we've got RS, we've got SU, we should have U, and the vector with U is UQ. And then we should have a vector beginning with Q, so this is QR. And so this should form a four-sided shape, taking us RS, SU, UQ, QR all the way around. And we'll bring a copy of our diagram here just now. I know this is a luxury. I'm not expecting you to draw a separate diagram every time. If you use the single diagram method for nodal analysis, and you can draw a separate diagram for each node if you want, it will still work. But if we bring down our diagram here, we can amend this one rather than drawing over, so that when we look back, we can still see what's happening at every stage in the diagram. So let me move this over here just now, and I'll remove the arrowed lines, because again, when we're analysing a different node, the internal forces will be acting relative to that node. They're not universal, unlike external forces, which are. So already in this diagram, we have the cyan force here. This is a force acting down the way, so we can indicate our diagram that this is acting down like so. And we already know the force SU acts away from the actual SU, acts away from the node. So we can indicate that this is acting in this direction. For the arrow to look better. This is acting in this direction here along SU. So whatever else we add onto this diagram, we've got our first two forces in place. And it's at this point, I'm hoping you can see the advantage in using a single diagram. Can we start off, rather than having to draw in 4 vectors, we only have to draw 2 additional vectors. We have this already. Now, we have got 2 lines to draw in here. We've got a line QR, which is going to run through point R and has to act up at an angle of 60 degrees. And we're going to have a line UQ, which acts along the horizontal and has to connect to point. So we can choose either of these to join onto our diagram at this point. We'll start off with QR. And that means I'm going to take a horizontal line. I'm going to take it out of point R here. And when you're doing this on your own page, this is where using pencil can really come in handy. And I know that I need to measure up 60 degrees because this is 60. Oh, that is incredibly annoying. I didn't mean to do that. I'll see if I can fix the scale before I... It doesn't matter too much because we're obviously using the scale from the question anyway. I think that's about right for a scale, but this is one of the pitfalls of using the whiteboard. So I'm going to measure up an angle of 60 degrees from the horizontal for this line QR, which it must run in this slope, and it has to run through the point R. So I will change, I'll pick a new color here. We'll pick the color, I don't know if this is pink or magenta, one or the other. Let's use this one here. According to the, oh, what color did we use before then? Oh, according to the, that purple line was actually about, apparently this is purple. I'll call this magenta, this line, it's close to it. We have to have some line that's running through here. And I'm sorry if this color looks a bit similar to the purple color already. We've got some line here that's running through this point here. But the reason I don't need to go much further than this is because the line UQ is horizontal. So that means that a horizontal line has to run from point U to join with this point. So if we get out a ruler again and make it horizontal, we're going to use a yellow color this time and draw a horizontal line through point U that has to join up to this line that I've just drawn here. And this is where things that get a little bit messy, but I'll talk you through what's happening. So if we come from U to here, then we're actually coming back on ourselves in the blue line. So let's tidy this up and then let's take a little walk through all of these vectors. So first of all, this kind of purpley pink line here, I'll put that R back in a second. So what's happening here? We're coming down the line RS. We're traveling from S all the way along to U, because that is the vector SU. The point where the pink and the yellow line meet must be point Q. So this must be point Q here, because we had the vectors QR and UQ, so that's where they meet here. And so we're coming down RS, we're going along S to U, we're coming back along from U to point Q, and then we're traveling up Q to R. So this is our path. We're still going around our vector in the correct order, but we've just got to be a little bit careful when these lines start to overlap with each other, like so. So this is the path that's happening. We're going RS, S, all the way over to U, U back in the same line, but in an opposite direction to point Q, and then Q heading up to R. And so from this, first of all, we can take what all the natures of these vectors are. So QR, which represents the member BE, is heading away from the node, which means this is a tie. And we've got UQ, which represents member AE, and this is also, it's heading to the left, and so in the left on our space diagram means in the direction away from the node. So this means that BE and AE are both ties. So before we get into measuring them, let's add this to our table of information up here as well. AE and BE are both ties. So going back to our analysis of node E, we're going to measure these lines as well. Now my ruler's going to be out because I had that unfortunate zooming incident there, but it looks like the line UQ is about 1.5 centimeters, which would be 15 kilonewtons for member AE. And if I get my ruler lined up here, the line I've drawn in for QR looks like it is about 3 centimeters. meaning that member BE would have an internal force of 30 kilonewtons. And that, in fact, is the answer. But suppose knowing what the answers are and maybe seeing that my measurements are a bit closer than they actually are. So I can mark these in. The AE is 15 kilonewtons and the BE is 30 kilonewtons. So lastly, before we get into it, lastly, we will be finding out the magnitude and nature of member AB. But let's mark on our diagram here. Since these are both ties, the internal forces act away from the node at either end. So AE, the forces are pointing in the way, and the same thing in BE here. So we now have at nodes B and A information about all of the members apart from one. So we can pick either node A or node B to analyze, and they're going to give us the information we need. We'll pick node B in this case because node A, we have two vectors still to draw. We've got to draw in reactive force 1 and the line AB. But at node B, we actually only have to add one vector to our diagram and everything will be complete. But if you did it in node A, you would still get the right answer. It's just about saving ourselves some work where we can spot these things. So let's move down and do our final nodal analysis of this example. This is node B. I've labelled it correctly, and we have a member AB acting up in this direction, a member BC, that's meant to be horizontal, acting across in this direction, and a member CE acting down in this direction here. And the angles between these are 60 degrees, as we've established previously. We know the directions on these. If we go back up to our diagram and see what we've learned about what's happening at node B, the member BC is a strut, so it's acting towards it, and the member BE is a tie, so it's acting away from it. So we can put in the direction of our internal forces here. We can also put in the magnitude as well, because we've established this in previous questions. So this is 30 kilonewtons here, and this is also 30 kilonewtons acting down the way. Now, you might be thinking something already when we're going to have three forces in a triangle and two of them have the same magnitude. What might the magnitude of the third force be? And if you're thinking 30 kilonewtons, you're not wrong. But rather than just say that, we'll put some evidence in here as well. And let's also remember to label our spaces. So these spaces are going to be P, Q, and R. So I'll label that on our diagram also. And let's also name these in the correct order. So when we encountered the vector PR previously, it was acting towards another node, so that was RP when it was acting to the right. So when it's acting to the left, it's going to be PR. And when we encountered the vector between spaces Q and R before, when it's acting in the upward direction is QR, so it means that in this node acting down the way away from the node is RQ. And that's what we'd expect. If we've got a PR, we'd expect RQ to follow on from the letter, meaning that our final vector is going to be labelled QP. So let's, again, let's steal our ever more complicated diagram from the previous part up here. And we'll copy you. But this time we have a lot less work to do. I'm going to just again remove these arrows because we're dealing with a different node. So some of the forces are going to be acting in different directions. Try not to destroy the diagram. That's good enough. As long as we get the arrows off, it's this is point Q, where the pink and yellow lines meet. And in this diagram, we have two forces already. So we're moving from P to R. We know that already. So we'll draw an arrow here. And then we're moving from R to Q. So we've got an arrow here. So the final vector we need in to draw it is QP. The points Q and P are on this diagram already. So we're just going to invoke another colour. We're running quite low in pen colours. I think we've got a nice gold pen here, so we'll line this up. And I know this should be acting at angle 60 degrees from the horizontal line, but even if I didn't know that, I can see there's only one way to join these 2 points that are already on my diagram. So at an angle of 60 degrees, I'm going to use this gold coloured pen here and mark it in. And to complete our circuit of forces, to take us all the way around so there's no resultant, we can only be acting up in this direction here, which means QP must act towards the node, meaning that AB has to be a strut because the internal force is acting towards the nodes. So let's go back up and we'll record our final pieces of information here. The nature of AB is that it's a strut. We can mark that on our diagram if we want to. It doesn't particularly matter at this point because we've nothing else to learn, and we can go and measure AB as well. Now I'll get down to the final diagram, and whether it is or not at this point in my diagram, it's still looking pretty close to what I call 3 centimeters in my ruler, but it will be 3 centimeters because this is a 30 kilonewton force, and we can add that to our table at the end that we have found that AB is a 30 kilonewton force. So now that I've done all my measurements, I'm quite happy to zoom out and do a recap of how we solved this problem. We solved this problem by first of all finding out the reactive forces in the beam. Now, in most questions, you'll be told what the length of the base of a structure is. Here we didn't know it, but by calling it X, we could work out what the reactive forces must be anyway, based on what we knew about the distances along the triangle. That 104 kilonewtons must be 3/4 of the way between nodes A and nodes D as we look along the length of the structure. So we had these 2 reactive forces. We drew up a table, we labelled our spaces so we could name all our vectors, and we started at node D, which is correctly labelled now. I incorrectly called it node C to begin with. We started at node D and we worked our way around the structure. Starting at node D, because we knew the reactive force, we were able to identify what was happening in members CD and DE here. Then using this information, we can move down to node C, and because we knew the external force of 104 and we had the information about the member CD, we could build up a picture of our diagram and add in some additional forces represented by vectors RS and RP, which corresponded to CE and BC in our diagram. And we did the same for node E, and I won't continue to read all these out because we've done it in the video, but we can see we built up in our diagram and we're able to add in another couple of vectors, in this case UQ and QR, giving us information about 2 more members. And that meant we only had member AB to deal with, which in this case was represented by vector QP, and we were able to add that to our diagram. Now, when you're completing a question like this, you can continue to add to your diagram without redrawing it, and you'll end up with something like this at the end. And that's absolutely fine. Just make sure all the points where lines are connected. This could all be in black and white, it wouldn't matter. As long as you're labelled all the points, the lines are connected with the letter representing which end of the vector it is, it will keep you right there. So that ends the video. This is one of the biggest examples that we've done. Quite often our assessment questions, we don't get you to do quite so much work, but this is a pretty exhaustive example of how we do Bose notation in order to do nodal analysis, and how we do it using a single diagram, but I've built it up in stages to let you see the changes at each point.